All right, for the last few questions on homework 35, these are all calculator problems. So this says, complete the table for a savings account in which the interest is compounded continuously. So something you need to remember from pre-calc is that the amount in the account will be equal to the principal times e to the RT. So if I want to figure out time to double, I'm initially investing 4,000 at 6%. It's quite the savings account. So time to double. So we would say, okay, we're going to get 8,000 after a certain amount of time. We're investing 4,000 times e to the 0.06 t. So we need to solve this for t. So isolate the e term. This divides out to 2. To get rid of the base e, you natural log both sides. And divide by divide by 0.06. So we can see what that approximates to. I guess I don't have to use a calculator. I could just leave it like that, but just out of curiosity. So it's about 11.552 years. All right. And then for the amount in the account after 10 years, so that's where we don't know A, we're investing 4,000 at 6% continuously for 10 years. So 4,000 e to the 0.06 times 10. Oops. So that's 7,288.48. Put a dollar sign on that. I think this is what I said. Let me double check that. 7,288.48. Yeah. All right. So no calculus needed there. Just sort of a reminder about our compound interest formula. For this problem, the population in millions of a country in 2007 and the expected continuous annual rate of change, K, of the population are given. So this is based on actual data. Find the exponential growth model, which is this, for the population by letting 0 correspond to 2000. So, all right, so we have Latvia as our country. The population is 2.3 million. They're giving us the value of K here. So for part A, we're just trying to find the model. So that means we need to figure out what C is. Now, if 0 is 2000, that means that we would have a population of, let's see. Sorry, this is the 2007 population. So that means that we would say, all right, t equals 7 when the population is 2.3. So this is going to be 2.3 equals some initial population that we don't know times e to the negative 0.006 t. Oops, not t. 0.006 times 7. And so if I solve that for c, I would just be dividing. All right, so let's see what that comes out to. 2.3 divided by e to the negative 0.006 times 7. So that c value is 2.399. We can approximate that. I'm going to leave it on my calculator. I don't want to round it, but that's sort of the initial. So for part A, so our population exponential growth model is about 2.399 times e to the negative 0.006 t. Right, and then part B, use the model to predict the population in 2015. So find P of 15. So I'm going to use the unrounded version in my calculator. So I'm leaving this on here. So this is C times e to the negative 0.006, and then we're multiplying by, 2015, so 15. So 2.192, and then we label that million. This would be 2.192 million Latvians. And then part C, Discuss the relationship between the sign of K and the change in population. So K is negative, and we can see with our populations, we're going from 2.3 down to 2.192. So since K is less than 0, the population decreases as time goes on, or as time increases, whatever. All right. What about this bacteria growth problem? So this one says the number of bacteria in a culture is increasing according to the law of exponential growth. There are 125 bacteria in the culture after 2 hours and 350 bacteria in the culture after 4 hours. So we have a couple of ordered pairs, 2, 125, and 4, 350. Find the initial population. So to get the initial population, I need to have a model first. So, well, I think I do. I guess they asked me to write the model next. I'm going to go ahead and find the model. So exponential growth in general, we've got P equals A times B to the T, right? So we could say 125. Actually, let me make it C. Hold on. Let me use the format that they're usually using. Let's use C times E to the KT. That's fine. We can do that too. I was slipping back, and with pre-calc, we did A times B to the T. Okay, so this would be 125 equals C times E to the 2K, because 2 goes in for T, and the numbers are populations. And then we also have that 350 is equal to C times E to the 4K. Now, this is something that we can set up with the system of equations because we have 2 unknowns, and we can solve each of these equations for C, for example. This is one way to do it. So C can equal 125 divided by E to the 2K. And similarly, C is 350 divided by E to the 4K. So if I set these two equations for C equal to each other, I can work with them a little bit. Now, I would like to get the E's out of the denominator. I'm going to multiply E to the 4K up here. And I'm going to divide 125 over here. So when I subtract these exponents, E to the 4K minus 2K is E to the 2K. And what is 350 divided by 125? 2.8. Okay? And then we can natural log both sides so that we get 2K equals natural log of 2.8. And K is equal to natural log of 2.8 divided by 2. And then if we know K, then we also know C. So I found K. Now C is equal to 125 divided by E to the 2K. Now 2K will just be natural log of 2.8. So now that's just natural log of, or that's just 125 divided by 2.8. Because E to the natural log, because E to the natural log of 2.8 is 2.8. So C, the original number of bacteria, is about 45. So I'm going to call it 44.643. Leave that on my calculator. So I guess I've kind of done part B. So part B, I did that first. So part A, let's see. Part A, what's the initial? The initial is C, which is about 45 bacteria. And then part B, I've also answered. So my exponential model is P equals, I would leave this, I think, as 125 over 2.8, just so it's not rounded. And then E to the K, ln 2.8 all over 2 times T. And then part C is use the model to determine the number of bacteria after 8 hours. So find P of 8. And because part D is after how many hours will the bacteria be this, I'm going to do this by graphing, I think. 125 over 2.8 times E to the ln 2.8 divided by 2, times X. And then if I want to evaluate P of 8, I can do alpha trace of 8. So 2744 bacteria. That's after 8 hours. It's a lot. Okay, and then after how many hours will the bacteria count be 25,000? So I could solve this with natural logs and stuff, or I could just say, if I'm allowed to use a calculator anyway, we did this a lot in pre-calc. We solve things by graphing. And then you need to use, though, like for your window, you need to use your previous answer to kind of help you. So I know the x values need to be bigger than 8. I'm not sure how far out to go. So I'm going to go to like, I don't know, 20, see what happens. And then I'm going to zoom fit. I just need to be able to see the intersection point. So is this going to work? Oh yeah, this is going to work. So 20 was plenty. I could have gone smaller than that. As long as you can see the intersection on your calculator, it will be able to find it. So my answer is 12.292. So T is, sorry, I need to show some sort of work here. So you're showing P of T, when is that equal to 25,000? And that's when T is about 12.292 hours. Hours? Yeah, hours. All right. So again, I didn't really do any calculus in these last couple of problems. This was all pre-calc stuff. Are you going to have a lot of pre-calc on your calculus exam? Not necessarily, but it's a good reminder of, like, you definitely have to solve by, you definitely should, I should say, be solving by graphing on your BC test. And we will have functions that they probably give us. But sometimes we do, given 2 points, sometimes we do have to find our population growth, our exponential growth model. So it's good. It's good practice. Not super prevalent, but good practice. All right. Come into office hours if you want more practice with this stuff or if you have questions.